nice to see you. Welcome to this 24-hour global live event. It's my true pleasure to introduce you again. You have inspired much of this work, and it's wonderful to see you here.
Okay, thank you. It's my pleasure to be here. So I guess in the 40 minutes or so, I would like to just share what we have learned from mapping scientific literature, and also, as you see from the title, what can we learn? I will identify some important factors that we may take into effect. What is the process, and what should we do here? So before I start, this is some resources that if you like further details, here are some books relevant to these topics, and also have some links for journals as relevant to these topics as well, from the information visualization perspective, as well as the research metrics and analytics. So let's get started. So I'll start with this one. What do you see here? You have this in front of you, and I'm not really looking for answer, but here, look at this and think about what is the first impression coming to your mind. So again, here, what do you see? So again, different people may have different answers. And here, what do you see? So here's an interesting exercise I used in my class. So here are some representations of some relationships. You can see here on the left-hand side, we have several, 5 of them. One of them already identified as best friends from childhood. And you can see the characteristics of this kind of drawing, or we can call it visualization in a very broad sense. So here I'll leave the other remaining 4 for you to practice. If you haven't seen this before, you can identify which one is which. So this is probably the one I will try to underline here in today's talk. And so these are 3 equations, or equation-like statements. So with a violin and plus some music notes, and you add a player, and you get something. If you have a great player, you get a great piece of music playing. And similarly, the second equation is that you have some tools or paint brushes and the things you might need, and you add something else. With a great painter, what we get is a masterpiece. So what I would like to emphasize in this context is the role of different components in a science mapping process in this kind of activities. So science mapping as a process or as a tool. So we can look at this in a similar way. So you can see all the columns here. Science mapping tools will typically take scientific literature data as input, and then that will generate certainly lots of science maps, and you will see in the next 24, 23 hours, and lots of different kinds of maps. And then the other factor I would like to emphasize today in particular is the role of mental model. So the role of mental model is serving this purpose to interpret, to make sense of what we're seeing. What can we learn from these kind of maps or this kind of visualization? So put them all together, what we get is, I want to call it meta-knowledge of knowledge. So because the science is about knowledge, we're looking at the science map, so we're trying to figure out what's going on and what are the different kinds of patterns, trends, and so on. So these are the outcome of when you're adding all these components together. So the reason I put these 3 equations side by side is trying to make my point here. The role of player here, and in particular, what differentiates the role of player is really we can focus on the role of mental model. So I'll explain a little bit further on this particular role. And by adding all this together, we will expect to see a wide variety of different kinds of visualization, interpretation, and sense making. Different people get different stories, different values out of this. So this is in the broader context of science mapping. So to further underline what I will share with you is I like this quote in particular: the eyes are not responsible when the mind does the seeing. So I use all this very frequently for this in the context of information visualization and also in the science mapping context as well. So the emphasis is not only what we produce visually, but also what's in the player's mind. So the player can add a lot to this process. On this chart or on this slide, the good things are on the left, and the bad things we try to avoid is on the right. So what we're trying to get here is the insight, the patterns. We want to recognize different patterns, different trends, and then we want to make predictions. We want to be able to anticipate what's going to happen next, and then also we want to make our decisions, very well-informed decisions, and we take actions to achieve our goals. So those are the good things. The pitfalls and the traps or the potential limitations by looking at the same visualization or even using same tool, same data, what we may also get is biased and confused, misconception, misinterpretation, or frustration, and also so lots of that kind of experience spread across these two extremes. Something on the left is very good, and we want to get the most out of science visualization or information visualization in general. And also on the right, we need to be very careful about this as well. So again, we go back to this chart. I like this chart. It's the best friend in the childhood. You can characterize this. This is an abstraction. So the distance or proximity is between the two lines here. The childhood friendship means they're really close to each other and then generally drifting apart slightly over time. So the connection here is that we know we omit a lot of details where what we keep, what we retain, they are the key information, or they are the characteristic defining information that make what we believe this is really illustrating a relation between two people from their childhood. So along this line, in parallel, if we look at the questions on the right, the question we may need to answer or address when we're dealing with science mapping process is, you can look at here, do we know how science is supposed to work? So compared to the one on the left, we understand quite clearly how childhood friendship will evolve over time. So that's one of the important elements that make it possible for us to understand what we're looking at there. Even lots of information, lots of details we didn't show, we don't need to show. So here's one just example. I want to refer this back and forth just to highlight what is the really necessary information here when we're making this sense-making process. What does it take for us to understand what is the displayed science pattern or trends? So I want to also emphasize a few other questions. I might be able to highlight some of the advantages of using the tools, and also something that we might be able to avoid. So second question, for example, where shall I start? Suppose I know nothing or little, very little about a scientific topic. So what can I do? So what should I do with one of these getting increasingly popular science mapping tools? And then how can I get started with a single relevant but out of date article, probably very famous comprehensive survey paper, review paper, but it could be 10 years ago, 20 years ago. And how can I find the most relevant part of the scientific literature? So now we can compare this with a GPS. We know where we want to go. We benefit from the contextual information. We know what is in the neighborhood, what's around if we accidentally get off the route we have planned for. What can we find? So what kind of areas should I pay more attention? So one assumption is that, or at least in terms of everyone's experience, we don't have the time or energy to pay attention to everything that's been published. And so how do we make that selection? And then finally here, the last question, are there any generic mechanisms and patterns that are repeatable, that we expect to see them again and again, that will carry us to make this whole thing feasible? That's like the childhood friendship chart. That summarize lots of relationships or so many people. By losing all the details, by retaining all the defining characteristics, we are able to communicate something, the patterns like that very clearly. We identify something. So one part of the equation will be looking for the generic mechanisms and to see how often they appear in different fields and how likely we can anticipate something going to repeat again in the future. So that will give us some advantages in terms of what can we anticipate and prepare for the next move. So there's some the general question or statements here I want to put it. Maybe some people, when they first come to science mapping, they may be worried or think about several of these problems or the resources they don't have. So one of them, let me begin with this. So the assumption is you'll have to have a domain experts to help you at several stages of the process. So that's good. When you have a domain expert, that certainly you benefit from it. But without it, lots of science mapping tools can help you a lot. So by the lacking of the domain experts immediately accessible to you, so now these days the threshold has been lowered significantly. So I'll have some examples demonstrate to you. Without the immediate access to domain experts, what can we do? What can we achieve? So those are important things that we need to bear in mind. Second one is the belief that you don't need to learn the basics of scientometrics and theories in order to make good use of science maps. So there's a general feeling I sense from lots of people I talk to, the questions they have is that to learn about rocket science, for example, everyone agrees we should spend time to learn the basics, foundations, principles, and so on. But when it comes to science mapping, try to make sense of scientific fields or landscape and so on, lots of people don't feel the pressure to understand deeper what they are looking at. And so that's an element I would like to elaborate later on about this. So this is in part as a part of the player's role I mentioned earlier. We have to consider what the player can bring into this equation. So the other one, the other assumption or belief that only positive and supportive references contribute to scholarly impact. So that ignore the negative, the criticisms and the other kind of contributions to an impact or scholarly impact in particular in this context. And the published works in scientific literature, the last one, are settled once for all. And this is probably far from the truth or the reality. Is not settled. Once it's published, it's still there. It plays a role that continuously subject to later subsequent evaluation and improvement on top of that, and so on. So it plays a role once it's get into the landscape. So some problems or limitations when using science mapping tools. I, in particular, from my own experience especially using my tool, like tool I designed, here, lack of theoretical foundation and also lack of the knowledge of theories and what I call the mental models, which provide a guiding role to guide us what should we look at. So those are the guidances I believe are from the mental model, nothing else. The second one is often that we fail to consider multiple perspectives. We take one perspective and we could jump to a conclusion, and that's simple, that's easy to do. But in reality, we could do better if we can accommodate multiple perspectives, and especially competing interpretations. Both of them can be true at the same time, but how can we resolve it? And also conflicting opinions. And we want to identify what are the reasons, what make them reach different observations, different conclusions. That is the important part. So put it all together, we don't want to rush to conclusions. Most of the time, nothing is really conclusive. So that's especially in science, because science constantly change and moving. So that is particularly something we should delay our conclusive finalize what we see, what we believe, what we're seeing. So subject to changes and keep an open mind. So the last two is at the probably much higher level. I will touch a little bit on this topic of uncertainty, how the role of uncertainty plays in the context of scholarly communication, and what is the nature of that influence, the patterns or the trends we can see. And again, similarly, connect to this rush to conclusion. The other one is the other way to look at it is the accountability, responsibility, and transparency. And we need to put this into a broader context when we make our science maps and interpret science maps. So very quickly, I like this chart that emphasizes the volume of scientific literature. This is published in 2014. That was almost 10 years ago. And so the key point here from this chart is most publications never get noticed in terms of citation, never get cited. Only the top, very thin layer on the top, they get cited. So here, again, the selective question becomes more relevant. And here, where should we look at? So we can certainly say we would preferably looking at the top of the mountain, and that those studies already been reviewed by many peer reviewers and also by peer researchers, and so that we can build on a solid ground. On the other hand, it doesn't mean those are near to the bottom of the mountain has no value at all. We can safely ignore them. That may not be the case. So here we face this problem. What can we effectively using the scientific literature? There are lots of valuable information there. So here I like to quote this. This is from Bernal. In his book published in 1939, he mentioned this. I quote here, I think is still applicable today. Production of scientific publication has long ago become so large, it's recognized that the scientific worker can only read a small fraction of the papers. So, which is probably even more the case today. Here, I highlight in yellow is about how can he ensure that the papers he does read are those that to be the most valuable in his work, and how can be certain that it's not in fact reduplicating work already done. So if the same question has been addressed successfully in the past, when we overlook it in our search, and that could be something we want to avoid. So we want to know the most relevant studies has happened in the past that is relevant to our study. So here, this was 1939. At that time, the solution was to provide abstract to summarize. So you don't have to read along the full paper. You just glance to summarize the abstracts. But then that become a problem because the volume of that is become too big very quickly. So here's in this chart, I want to illustrate some of the complexities I put into this science mapping kind of behind the scene. We're looking at the data and what the data, how can we select those relevant data. So here, one example is suppose we're interested in the mRNA vaccines, and there are lots of papers. Here, if you can do a different search, you get keyword search. At that time, it gave us 434 related papers or relevant papers. And from there, the most cited paper, for example, that happened to be a review paper, systematic review or survey of this topic. And that paper by itself cited 222 references. So this is still within our humanly possible reading power to read 220 papers and to understand what's going on. But if you look at this in a broader context, take one step back, that very important research paper has been cited by, at that time, by over 500 papers. Those are more recent, more relevant to, for example, we can imagine to the current pandemic, the vaccines, and so on. So from here, we can also expand this to a much larger, wider variety of other kind of studies we may never anticipated. We never thought there were some other studies may be relevant, but it's not clear at this point. So purely based on the citations, the one paper referenced the other paper, purely based on this link, we may quickly expand this to 23,000 papers because of some overlap in terms of references they cite and the references cited by this RC paper. So from this single seed paper, we may pull out, we can cast a net. This net, we can catch over 23,000 other articles. Now this started to go beyond our reachable time, the time we have to read 23,000 papers. How long that will take? We don't have that time. So this is the kind of the context we have for science mapping in reality, in our research, in our everyday research. We need to find some ways that we can quickly narrow down to the most relevant ideas, the most valuable information out of this relatively small mountain of papers. So here the question on the top, we can generalize all these questions. So what is the broader context of the topic? So given the topic starting point from here, what else are relevant to our search? Secondly, how this already extended, which is sometimes called our basis or intellectual base of our particular work, what is the context of that set? And similarly, what do the most visible works cite? I mean, the currently what the most visible works, how do they stand out? Where are the ones that appears more valuable than others based on certain metrics? And so these are the considerations. We can streamline them so that we can provide all different helps, indicators, and also patterns, put them together. But from here, what I want to emphasize is indicators by themselves are not enough. So we have to think about our mental models, the role of that, and how our mental model fitting to this workflow or landscape. So here I will use a SciSpace as to illustrate this process and to illustrate the role of a mental model as well. So for example, let's say we are interested in some topic, we start with a query and we get some data sets. Then SciSpace will break down this into something called time slicing, which basically year by year create a network and then stitch these networks together, and we get an overview. So on this overview, we can have some different kinds of views, clustering, and then we can label the clusters automatically or up to this point. So the next issue here in the face is when we look at pictures like this, where should we start? So that's the question always faced with looking at a map. Where should we start? We know where we want to go. How can we get there? There are some possibilities. So that's very similar here in this context as well. So I want to mention here the mental model is the key that guide us to pay attention. What sort of patterns should be there or anticipate? We should pay more attention to certain kind of patterns, and where we can also ignore some other noises or other kind of appearances, and then leave them for later or deeper investigation. So at the higher level is that I think Ben Schneidman has this mantra many years ago: overview first, and then the next step after overview, get an overview, is to determine what is the area of interest, or what are the areas of interest. So where do we go from an overview to a specific area? What kind of patterns are important to us? So those are the things decided by our mental model. So here I want to share with you some examples we have in terms of what we have learned, and then I will follow this by what we can learn from scientific literature. So one thing we have learned by looking at this visualization, this is one of the two case studies appeared in the 2006 paper. The reference is in the lower right corner. So at this level, we can see the two things, observe two things. One is this one. This is a stream, lasts about 10 years. And people or researchers there, they were looking for the answers to this question, how dinosaurs extinct, what make dinosaurs extinct. So they're looking for answers, lots of theories. At this point, there are more than 80 theories in early 1980s, around here. This is one of the theory that survived. So people follow that. So we can see here roughly this this stream end about this time. So that's when they found a crater, some conclusive evidence that support that theory. So here you can see there's another one appear slightly earlier than that. So another one appear here applied to a different mass extinction. There's an earlier mass extinction. This is 65 million years ago. This is 250 million years ago. So applied to that, so the pattern we can observe at this level, this is quite above individual publications. This is like the a view from looking at this research community, what they're doing, what their activities actually changing. So what I like to emphasize here is a few things. Why this is so special here. So if you look at this, let me see my, here the player. Remember the equation here, we have a player. In this case, the player, which was me, I'm not a domain expert in mass extinctions. And so, but I use this tool to make that observation. So the shift from one research stream to another. So the other one, the other factor here is the study we published here is 2006. We make this observation based on the successful experience, applied theory, applied to that, and researchers realized this is the time to move to another research topic or research area, but using the same, almost the same research method. So this strategy worked once. They want to apply this to a new or much older mass extinction case. So if you look at the second one, this is a paper published in 2010. They are the domain experts. They published, this is a very comprehensive review paper. They, if you want to compare what they said in their paper, what they said in their paper is almost equivalent to what we observed. So for example, numerous workers have searched for evidence for similar connection. So which means that's the similar strategy to apply the theory to the search for a crater. So that's what they do. And so the emphasis here is we reach very closely the same observation here. And we can reach that conclusion or the observation a few years, even we have any other sources to support our observation. So that was very encouraging for us. So one of the the points I want to emphasize here is evidently we can achieve this by carefully analyzing the patterns and trends appeared by the study of scientific literature without the domain knowledge. So certainly my domain knowledge at that point is 0 compared to with the domain knowledge of this review paper. But then here, this is first case. And here's the most recent version created by SciSpace. Well, if you're interested in this topic, it's a fascinating topic by itself. So you can look at this topic and identify over time how focus of the research community change over time. And here these labels are generated computationally, again, to minimize the need or the pressure. You need to know a lot. You don't have to know a lot about this, but so the focus is not really on what is not explain why something is important, but rather as the first step is to focus on what is something that might be significant. So certainly we can look at those. There are several theories as well. But importantly is to delay the time we can reach out to a domain expert. So before that, we can still make a lot from this data. So here's one example. Some of the links, this is called the link walkthrough in SciSpace. It highlights at certain points, the researcher's behavior is really agreed or consistent together what have the relevant areas should be involved in a particular year. So this is valuable information for us. Even this is not our own research area, but if you can see, we can apply this to many different research topics, research areas, so that we can capture what is the dynamics of a research process, what's everybody's focus, attention currently is in the scientific literature. So the second example we have, what we have learned is from this generative medicine. You see, this is a different topic, different from mass extinction. But again, this is also a good example to show, again, we are still the domain, not domain experts. We have no knowledge about this domain either. So we intentionally choose such kind of domains to test how far we can go. So without knowing too much about, not too much, without knowing almost nothing about this regenerative medicine, we can identify some key moment or time the network structure is undertaking some significant change. We don't know what change that is. We just know there's some change. So that is important first step. So here, based on the network, the advantage of using network is actually we're pulling in the expertise from numerous authors. They publish, they know the domain inside out very well. This is kind of folksonomy, folk sourcing, and we get lots of signals from there point to something important, and we simply follow their signal. So in this table, we use a measure citation burst. Many of you are already familiar with this. And so this one, we published this in May in 2012. We're very pleased in October 2012, when the Nobel Prize was announced, that these two papers actually responsible for that Nobel Prize discovery. So the third case, again, is this area we don't have much domain knowledge either. So this one is much older. This published in 2004. So in this case, actually the first time we created, we're using metrics or identify this one. Here, I put it out with my hand. So this one stand out. That's not what we anticipated. We're looking for something else. We had the paper, we found a paper written by domain experts about scientific revolutions, two revolutions. We were preoccupied to look for the second revolutionary paper, but this one keeps standing out until we didn't pay attention until later on. What is the role of this one? Why does one keep stand out even more visible than anything else? So we published that in 2004, but this one later, as you can see here, this work several years later, in 2007, it got its recipient of several awards later on. And then we will compare what they said about why this one's so special, so particular, and the contribution. And then we realized this is actually retrospectively, that's a good example we have identified. We just so preoccupied we didn't focus on this one at that time. So again, this one's domain knowledge, we don't have any here. And also the timing is 3 years before, at least 3 years before the 2007 award. And this one identify a mechanism is called boundary spanning contributions. I would like to give you a few more examples after that. So in terms of the mechanism, here I was dreaming in 2011 as if we can find some mechanisms for creative thinking and problem solving, and those mechanisms supposed to be repeatable, then we can benefit a lot. Even we can just capture a small amount of all the creative activities, if we capture one of them or some of them using a single mechanism computationally, and then we can go from there. We can save a lot of the time and effort. So that's the part we need to again pay more attention to the role of mental model. So the role mental model here is, in my sense, it's just you have multiple perspectives, multiple theories or models about how science can change or how scientific knowledge is developed. There's so many of them. So for example, from philosophy, sociology, psychology, and almost every field, every discipline, they have some theories about how science should or is supposed to work, to develop. So one thing I would like to start from here is that we notice the red bars here, they are the citation bursts, the period of citation where suddenly they get lots of citations. But then here the trend is clear that the focus or the papers that get highly citations, they shift over time. So this we'll call it attention space. The dynamic of this attention space is that we keep changing the one we're looking at. So maybe this is common sense, but it's very insightful from our own perspective. We're looking at this, then we realize for science mapping process, we may expect something like this spread out, but the focus will be different over time. So here's one example. At this particular time, the whole focus is really on where the links, the bridges connecting two fields or two topics, you see the concentrations of these topics. And here you can see another point of time and focus suddenly shifted. And the older references or older studies they're not mentioned or cited as much as the new ones. So at least our knowledge advanced. We know probably something better, something different. So then the movement or the dynamics of the attention space could be created by internal or external triggers. So we're looking at this first example, some triggers, external triggers. These are the terrorism research. And that research field, certainly some triggers, including the earlier Oklahoma City bombing and September 11. Those are the external events. They happen. Research the landscape changed a lot. So in terms of internal triggers, there's some models or theories about this as well. So simply speaking, is a 4-stage model. So one start with a question, and then to build a tool. And once you have the tool, you apply the tool. So application, and you codify the knowledge. So those are simple models of what could happen internally, just based on what is the original purpose of the research. So another part of the mental model role could be played by something like a philosophical theory or history of science, scientific revolutions. So this is just one example. You can, there's so many theories like this available, but this is one of the most influential. So another point here, when we look at this, this is from NSF, a project called the Traces. This one is an innovation here. When we look at this, innovation can take lots of time. But one thing, let me get this. One thing the pattern emerge is that there's almost no connections across these kind of channels. They keep going in one direction until by accident or much later, there's some connections. They figure out there's a connected, we should be able to make use of something from a different area. So this is a challenge. This is always a challenge. We're looking for something we don't know, and you can imagine what is the efficiency or the inefficiency of that. So here's some clue that where we can find the ideas or creative ideas. This is from philosopher Collins. He said creativity is really, you can expect this one found in the fighting, the battlegrounds of different schools. They have different opinions, they have competing hypotheses or competing paradigms, and those are the areas the most likely you find high quality ideas. So another thing we borrow is from the analysis of the social networks. This is from structural Hall theory. And structural Hall basically says this is a structure, and here, not everyone is equal in terms of the information exposed to the different kinds of information. The more, the better in our case. So let me see, I'm looking at the time, I'm running out of time. So here, we borrow this idea, structural Hall. We look at the scientific literature to see if we can find similar patterns or structures. So what would that mean to us? And what would that mean to the scientific community? So this is a verification, and there's some special transformative work in those areas. And so we can see all these type of things happens when they have these bridges connecting different areas of research. So going further from here is what would that mean if you see somebody's building a bridge across, making connections between those areas? So here's one example. This paper later got Nobel Prize. That's 40 years later. But if we roll back the time, we see that before that publication of that paper, we can see some clusters, we can see some islands. There are no connection, no strong connections, at least there. But that paper in particular, for whatever reason, the connection have this pattern. They link different two islands together. So this is what we call the boundary spanning mechanism. We're looking for this type of thing. At least some of them, they are recognized later, 40 years later, as a Nobel Prize winning discovery. So there's a paper. Again, we analyzed 3 cases of that. And so at least we are confident now, at least some small amount of scientific work are driven by this mechanism, or if we follow this mechanism, we can identify some important works. So I think this is, I have 5 minutes left, 10 minutes left. So let me quickly go through some other points I want to make very quickly. So here's one network of literature. And the starting point is one paper. But we realize one paper usually just not enough. We want to expand it. So this is one way that we can start with a single research paper we have at our hand, and to look at the neighborhood and what the other areas that we may be interested to visit. So this is what we call the citation expansion. And okay, I'll make it simple here. The expansion sometimes can go, can reveal very interesting thing we will never get by any other ways. So here's one example. The original area, we started here by expansion. We can see there's a very thin line over there. We end up with include another area. So I think that I'll leave this as the final topic here, the uncertainties. The uncertainty is they stay in scientific literature all the time. But so far, many of our focus is not emphasize uncertainty. Rather, we strip off the uncertainty part. We emphasize the one that is stable. So I will have the little bit summary here. This is a table that how often, how common this uncertainty is can be found in every paper, almost every paper published here. So uncertainty, I think we can understand what is the landscape and how we color or shape the different levels of uncertainty for different topics, different areas. I think I will fast forward some of these slides. And certainly like this, we can identify the citation context when people cite, and in particular, the opinions, competing opinions, and they cite reference paper. That's almost finished now. So I'll leave these concluding remarks here. You can take a look if you want. So in summary, the process of science mapping I just characterized is a complex, and there are several components that we need to pay attention. The role of tool, the role of data, and the role of player, and what we get from that. I think I better stop here.
Okay, thank you so much. That was great. We have a few questions here. First off, how did you get interested in kind of tracing these trends in scientific literature, following these patterns of thought? How did that get started for you?
Okay, yeah, that one I thought about it as well. So I started by the earlier research I studied on hypertext. So at that time, there are lots of experiments, lots of studies about the usability of hypertext and functions this way and that way. I found some inconsistencies in the literature. So some studies recommend this, some studies recommend that. So I just want to get some sort of surveys. What's everyone put together? What do I get? So that led me to a meta-analysis. We did the first meta-analysis to summarize that. And then that got me interested in this direction to look at scientific literature as a whole to accommodate different opinions, different insights from different sources. So I think that's how I got started on here.
Nice, thank you. Another question we have, what are the best tools for creating a map of science?
Well, that's a good question. It also depends what your need. So I mentioned here, I'm particularly interested or try to support individual researchers. If you have a specific research question in your mind and you want to get a quick start to see what is available, what has been done so far, and I would recommend you can search for Web of Science, Scopus, and take one of these science mapping tools, including SciSpace, maybe other tools. Getting more tools these days. But the question here is, I want you to pay more attention to the theories you're in your mind, what you're looking for. So if the general question is, I want to start, give me a picture, what is the most important thing in the field? Then a bigger map, and you can see a global map, and that may be useful. But if you just want to get more specific research questions, then you maybe just any tool should be, you could try whatever is suitable to you.
So thank you. This question may be an impossible one to answer, but what is your, you've published many books. Do you have a favorite and why?
Well, those books, one cannot replace another. So I try to recommend the recent one, representing scientific knowledge, the role of uncertainty. That's more about uncertainty. But the fitness of the information, the other one, quantitative assessment of critical evidence, that's also target the mind. And so both of them, I recommend both of them if you want to allow two favorites.
I suppose it's like asking you to name your favorite kid. You don't want to do it out loud. And then finally, you're the editor of Information Visualization Journal. What do you do as an editor? What are your tasks?
Oh, to collect, to generate papers. And yeah, that's a great question. Well, welcome contributions. And you make your footprint in the scientific literature. You make contribution, you share with others. So again, the spirit of science is the transparency of what you do, what you did. So you communicate, you share with us, and that's what I do.
Wonderful. Well, thank you so much for spending this hour with us.
My pleasure.
I think we're going to head over in just a couple minutes. But thank you so much. That was a wonderful talk, and we're grateful that you gave up an hour of your Saturday during a busy time. So thank you very much for spending this hour of the 24-hour mapping event with us.
My pleasure. Thank you.
Okay. Okay, there you go.
This was great. I'm so glad we got this all recorded also, because I don't think there's anyone out there which can really do all 24 hours, but that's why it goes around the globe, and that's why we are recording it. And it's really, really marvelous to have so many cool speakers on one day or in one 24-hour time slot. We are doing this live for 24 hours. Again, what we will also do is to post some of the links to Xiaomei's books, but also to the Information Visualization Journal into the chat so that you all have it. And I hope you consider submitting to the journal, but also please do read Xiaomei's books. I think he has just had a chance for a glimpse of this rich knowledge that he has and that his team have to present that in this 1 hour, but to benefit from all of it.